Hello class, and welcome to week 3. This week we will be learning about one of the most commonly performed programming tasks, the search. Either we're using our favorite search engine like Google, Bing, or Baidu, or we're simply looking for the file or folder by entering its name in a Start menu search box on our PC. Either way, we're performing a search. However, this week we will try to see how a machine can learn from the search and how it can use such knowledge to improve its results. There are many different definitions of a search. Everything from the simple search for an object, like your keys or a lost cell phone, to an internet search where we're looking for information. It's all considered a search. In this lecture, searching means searching in an internal representation for a path to a goal. Search proceeds by repeatedly selecting a partial solution, stopping if it is a path to a goal, and otherwise extending it by one more arc in all possible ways. One general definition of an intelligent action would be a state space. A state space contains information that would help us predict the effects of an action, as well as determine if it's the current state is the goal state. We can say that state space search bases its search on the assumption that the agent has perfect knowledge of the state space and can observe what state it is in. In other words, you can see all of it. The agent has a set of actions that have known deterministic effects. Some states are goal states, and the agent wants to reach one of these goal states, and the agent can recognize that goal state. A solution is a sequence of actions that will get the agent from its current state to a goal state. For example, if we have a pizza delivery drone located outside of the pizzeria at position 0103, and the goal is to get to the address 0123. A solution is a sequence of actions that will get the drone to address 0123. The more complex problem would be for a drone to have multiple stops between two addresses, delivering different items at each stop, until it reaches its final destination, 0123. A state space problem consists of a set of states, a distinguished set of states called the start states, a set of actions available to the agent in each state, an action function that, given a state and an action, returns a new state, a set of goal states, often specified as a Boolean function, goals that is true when there is a goal state, a criterion that specifies the quality of an acceptable solution. For example, any sequence of actions that gets the agent to the goal state may be acceptable, or there may be costs associated with actions, and the agent may be required to find a sequence that has minimal total costs. This is called the optimal solution. So with that pizza drone, if we had a sequence of actions that said to get to address 0123, and it doesn't matter whether the drone uses up power or flies into someone else's neighborhood or violates traffic laws, they can get to the goal state as quickly as possible, and any way to get there is acceptable. However, if the pizzeria has to consider the costs of possibly running out of power and losing the drone being hit by other drones, the drone flying into airspace where it's not allowed to be, then you must look for a sequence that has the minimal total cost to the pizzeria, and then the pizzeria has found the optimal solution. Directed graphs consist of a set of nodes and a set of directed arcs between nodes. In the graph, by nodes we represent states, while with these arcs we are representing the possible actions. The idea is to find a path along these arcs from a start node to a goal node. The path is the sequence of arcs, where between two nodes there is an arc from n-1 to ni for each I. If there is a non-empty path where the start node is the same as the end node, such path is called a cycle. A DAG is a graph without any cycles, or called a directed acyclic graph. A tree is a DAG where there is one node with no incoming arcs, and every other node has exactly one incoming arc. Roots and leaves are nodes with no incoming arcs, and it's also called the root of the tree, and the nodes with no outgoing arcs are called leaves. A problem determines the graph and the goal, but not which path to select from the frontier. This is the job of a search strategy. A search strategy specifies which paths are selected from the frontier. Different strategies are obtained by modifying how the selection of paths in the frontier is implemented. These are the breadth first search, or BFS, the depth first search, or DFS, and the lowest cost first search, the LCFS. In breadth first search, the frontier is implemented as a FIFO, first in, first out queue. Thus, the path that is selected from the frontier is the one that was added the earliest. Breadth first search starts at a given node, which is at level 0. In the first stage, we visit all the nodes that are at the distance of one edge away. When we visit there, we can paint them as visited, the nodes adjacent to the start nodes. These nodes are placed into level 1. In the second stage, we visit all the new nodes we can reach at the distance of 2 edges away from the source node. These new nodes, which are adjacent to level 1 nodes and not previously assigned to a level, are placed into level 2, and so on. The BFS transversal determines when every node has been visited. To keep track of progress, we can, with breadth first search, color each node. Each node of the graph is in one of 3 states: either undiscovered, discovered but not fully explored, and fully explored. In depth first search, the frontier acts like a last in, first out stack. The elements are added to the stack one at a time. The one selected and taken off the frontier at any time is the last element that was added. The basic idea of depth first search is this: it methodically explores every edge. We start over from different nodes as necessary, and as soon as we discover a node, DFS starts exploring from it, unlike BFS, which puts a node on a queue so that it explores it from it later. The simplest search method that is guaranteed to find a minimum cost path is similar to breadth first search. However, instead of expanding a path with the fewest number of arcs, it selects a path with the minimum cost. This is implemented by treating the frontier as a priority queue ordered by the cost function. This concludes your Week 3 lecture. Please take the time to browse your reading, to study each of the slides and the links that were provided before you start your discussion, question, and assignment for this week. Have a great week. We'll meet again in Week 4.